Hello everyone. For a couple of minutes I'd like to discuss the speeding up and slowing down rotationally activity. So if you would get out your activity packet, please. This looks like a long one, and it somewhat is. We started to learn about uniform angular acceleration, and I wanted to do a lab where you get some hands-on experience with actual rotationally uniformly accelerating object and a device, very high-tech device to allow us to make graphs and so that we can see all the graphs of it, right, and make predictions and things. This is very similar to a couple of activities you did in honors, right? So notice here that the equipment is being run by Data Studio. It's being run by Data Studio, not by Vernier, so you're going to have to follow the steps here in order to find the file, which is called Uniform Angular Acceleration. Right? You have to go to the shared drive, Cartoonist, Data Studio files, AP Physics C, and then rotation, and there should be a file called Uniform Angular Acceleration. When you open that up, it is essentially going to be a stack of rotationally kinematic graphs. You're going to have an angular position versus time graph, then an angular velocity versus time graph, and then an angular acceleration versus time graph. Right? As long as everything is set up and turned on, you should be able to hit the button and see all three graphs being made in virtually real time. What you're using here is a device that looks like this over here. This is a picture from the top of it. Okay, this is the rotary motion sensor that you've heard me measure or heard me mention before. Right? It measures rotations of this thing attached to it on top. Okay, and this little bar with the two masses here. Now this time we have it set up with a string wrapped around the pulley, the biggest part of the pulley, and then it runs over a second pulley, right? These are called super pulleys by the company. And there's some masses hanging off to the side that you can't see here, right? And those masses provide the torque, which makes everything angularly accelerate. Little Newton's second law thing that we'll investigate more fully later on. You'll notice that in case one, this is called speeding up in the counterclockwise direction as the mass falls. Right? So in this case, when you let the masses go, so that they fall, right, you should see this thing rotating counterclockwise. If it's not, you've got the string wrapped around the wrong way and you got to change it. Notice how the string kind of comes off tangent to the pulley. See how this super pulley is at an angle? It's not flat on there. Okay? This helps your masses to not fall off, the string not to come off the pulleys. So you need to have it turned like this. Should be set up like that now, but as you change it later on in the lab here, in the activity, you're going to want to make sure it looks like this again, right? That's why I gave you the picture. So this is basically a lot like a lab we did called speeding up and slowing down with carts going up and down hills a while ago. First step is always watch the apparatus a couple of times without starting the computer. Just kind of watch the motion of this thing. Right? So as the mass falls and you let it go, so you're going to wrap it up carefully, right? As the mass falls and this rotates counterclockwise, watch the motion. Then, with your group, try to make a prediction. Right? And actually try this. The point is not to get done super fast. The point is to learn. So what do you think the angular position, angular velocity, and angular acceleration graphs are going to look like? And then second, then you're going to run it, okay? And you're going to see what they actually look like. If they match, great. Hopefully by the time you're done with this, you'll be, much better at graphing these uniform angular accelerated motions. But if they don't match, that's not a time to just erase your prediction, right? This is when you then have to discuss with your group, why do my graphs actually look different than the ones I graphed here? Now, please be careful. I don't want the schmutz, right? I don't want the part before you let it go. I don't want the part after you've caught it or stopped it, right? Or after the masses hit the table or something like that. Okay, that's not what we're looking for here. Okay, we are looking for it while the mass is falling. Okay, should be nice smooth graphs. Once you understand why they're shaped the way they are, here's some questions that you should answer that might help you see why they are shaped the way they are. And then there's a few questions down at the bottom. Do the entire page before you go on to the next part. all right? Entire page. The second one is a little interesting. This is slowing down in the clockwise direction as the mass rises. So in this case, you're going to put the mass, you're going to lower it until it's at table, right? But the string is tight. And then you're going to give this a little spin. Okay, give the bar a little spin, and that's going to make it rotate clockwise, a little clockwise spin, right? And the mass should rise in this case. Okay, the mass right here should end up rising. Oops. Let me get rid of that and get rid of that. Will you go away too? I don't want to create a PDF. Oh well. Okay, and that mass should rise, and then you want it to, don't like, whip it around so that it's going to smack into it at the top. I want it to smoothly slow to a stop. So ideally, before the mass hits the pulleys, right, it should stop. And in this case, it says stop the apparatus when the hanging mass is at its highest point. That's when it stops, before it moves back down. I only want the part of the motion where it's rising. Follow the directions. Okay? Big hint here in the graphs I gave you to fill in what they're going to look like. Okay? Realize these are vectors. And again, you're going to make a prediction, see what it actually does, discuss, answer the questions. Now in the third one, I want it to speed up in the clockwise direction as the mass falls. Do you notice how this is changed? Look at that picture and look at the previous one. See, so the string has to get wrapped the other way, and the pulley has to get turned so that the string comes off tangent from the other side. As you might imagine here, as you let the mass fall, right, this is going to rotate now clockwise, right, and speed up, basically. Same kind of pattern. Number 4, same setup, except this time it's going to rise, so you're going to have the mass down on the table. You're going to give it a little torque. Please, again, you only want it to go up and stop. You don't want it to smack into the masses, otherwise you're breaking very expensive equipment. Then there's a summary page that I want you to do. The summary page is going to help us understand what does a positive or a negative angular acceleration mean. We're looking for patterns. And then number 5 is just for fun. Leave it the way it was set up for 3 and 4. This time you're going to give it a little counterclockwise torque, and you're going to let it go up and come back down. Ooh, fun, right? Let it go up and come back down so you get the full range of motion. This would be analogous to giving the cart a push and letting it go up the hill and come back down the hill. Again, I don't want the schmutz after it comes back down and hits the table. I don't want it while you're twisting it, right? I want it while it's moving on its own, right? So as it rises and as it falls, okay? And you'll notice here the little dotted line represents the highest position. More questions. So this is basically what you're doing, okay? If you got questions, of course, call me over as you're working. There is a key available, but I would ideally like you to try this without the key, right? Do a whole page. And then if you need to, it might not be a bad idea sometime to check, right? Because if you don't agree with the key, that means you either didn't have something set up right? If the computer is giving you a different graph than what I think it should be, because I know what I'm doing. So make sure you check the key as you do this kind of thing as well. And that is the speeding up and slowing down rotational activity.